We're going to lead off with Ray Simpkin. Now, he's been an active innovator and researcher since 1982. Some of us actually remember 1982. Rob Muldoon was Prime Minister, E.T. was the big film of the year, and the All Whites, all energy and long sideburns, went to the Football World Cup finals. It seems a very long time ago. His most recent research interests have focused on the use of hyperspectral imaging techniques applied to New Zealand horticultural and food-related sectors. Ladies and gentlemen, please welcome Ray Simpkin.
Thank you, Jeff, and thank you to the organising committee for inviting me to speak here. My talk is about hyperspectral imaging for horticultural applications. Some of you may have come across this technology already. Just before I get into the body of that, I'd just like to say a few words about the organisation I work for, which is Callaghan Innovation. We're New Zealand's innovation agency, and we're dedicated to these three things. We partner with ambitious New Zealand businesses of all sizes, connect and enhance the innovation system, and we activate innovation and accelerate commercialisation for a better New Zealand. The services we offer can be summarised here, the core services, basically four types of thing we offer. Research and development, which I'll talk about in a minute. We also offer skills programs. You may have heard of the Lean program in particular. R&D grants you'll also probably be quite familiar with, and this now includes the R&D tax incentive scheme. One of the new things that we've launched recently is this thing called Scale Up New Zealand. This is a free online platform where we invite businesses and innovators to actually sign up details so that they can connect with each other and collaborate. In the future, we plan to actually incorporate research providers into that as well. So this is the part of the organisation I work for, Research and Technical Services. We have some 200 scientists and engineers based around the country, Wellington, Auckland and Christchurch. 4 technology platforms we divide ourselves into: advanced manufacturing, biotech, advanced materials, and the group that I work in, which is IoT and data solutions. And IoT is Internet of Things. Within that group, there are a number of teams. I'm in the transducers and sensing team. So without further ado, hyperspectral imaging, what is it? Well, it's a hyperspectral image really consists of a conventional 2D image, but it's a 3-dimensional set. So we've got maybe one of those 2D images, but it's replicated several hundred times over several hundred wavelengths. So rather than just have ordinary 3 colors in your conventional camera, red, green, and blue, we might have several hundred. So this is the cameras that we use are basically a combination of a spectrometer and an imaging device. So the data that we acquire is called a hyperspectral data cube. So that's for each 2D image, we've got this 3rd dimension of wavelength, the spectrum. So each pixel in the image has maybe several hundred wavelength data points. So these data sets can actually be quite large, and they're very rich in information. So how can we actually use this? I'll just talk a little bit about some of the equipment we've got in Callaghan. This is really suitable only for ground-based image acquisition. This is a deliberate choice. We're not interested in drones or airborne platforms. This is one of the main cameras we have, the Pika NIR camera from Resonon. This covers wavelengths that you can't see with the human eye, 900 to 1700 nanometers. Typically sits on either a turntable or a linear scanner, and we've used this often outdoors in orchards and paddocks. We've also got a similar camera that operates over the visible part of the spectrum and just into the near-infrared. And we supplement that with what we call a broadband snapshot camera. And this is a camera that is not color, it's just a black and white camera, but it's sensitive to all these wavelengths for the full range, 400 to 1700 nanometers. And we typically use that with bandpass filters. So how can we use this data? So the cameras themselves are very expensive, and the one I showed you first is about $90,000 worth. So we don't really regard these as being suitable for putting out in the field or in an actual industrial vision system. But what we do is use the data that we get from them to actually help us design what we call multispectral systems, which might only work at a few wavelengths. So I'm going to talk about 2 different ways of using the data. And this is really based on some of the R&D projects I've been doing over the last 3 to 4 years. And the ones I've chosen, I hope you'll find relevant to NZ horticulture. So firstly, we can use this data to enhance the contrast of an object to actually make it more visible. And also, the second type of analysis we can use with this data is quantitative attribute estimation or classification. And this is a much more intensive computational exercise, and we usually have a set of ground truth data or training data with which to compare the spectral data with. So in terms of applications, I'm going to look at 3. Harvest estimation of fruit, and I'm sure the fruit growers in the audience will appreciate just how important that is. Disease detection in grapevines, and a bit of weed detection and discrimination. So contrast enhancement, early harvest estimation of fruit. I'll just show you this image. This is an avocado tree, and it's got fruit on it, although you have to look extremely closely to see the fruit. So if we wanted to have a vision system, an automated system of counting fruit, we'd actually struggle to use conventional color photography here because there's very little contrast between the fruit and the leaf. And a similar situation occurs for a number of other types of fruit as well, citrus fruit and apples. So this is an experiment I did in the lab. So on the bottom right there's a conventional color photograph of an avocado and its leaf, and you can see how close those colors are, quite difficult to distinguish. The top left-hand one there is taken with one of the hyperspectral cameras, and that's looking in the sort of longer wavelengths of near-infrared. It's a false color image, but you can start to see that there are some differences now appearing between the fruit and the leaf. And what we can do is that we can choose a pixel, and those 2 red arrows point at pixels, and each of those pixels has a reflectance spectrum associated with it. That's the amount of light that's reflected back, and we can display that intensity versus all these wavelengths. So you can see that the avocado one on the top right and the leaf spectrum, there are some differences there, and that explains why there's now starting to appear a color difference in that false color image. So we can exploit this. So this is a little montage putting all the data together. So on the left-hand side, conventional color photograph. In the middle, a false color NIR. And on the right is what we call a ratio image. So we pick 2 wavelengths of interest and literally divide one by the other mathematically. And what you find is that, as you can see from that bottom right, the fruit is now appearing as if it's glowing like a hot piece of coal, and the leaf is very dark. So that we've now enhanced that contrast. So we can use this to help us in the orchard. Here's another example with apples. The one in the middle there is a conventional color photograph, a red apple, a green apple, and some leaves. And there's also a white plastic Teflon sphere in there, which we use as a white reference. So the one on the image on the bottom right is the hyperspectral image, the ratio image, similar to the one that I just showed you for the avocado. The other 2, top left and top right, they're snapshot camera images, but with just one filter. So there's one filter for the left-hand image, another filter for the right, and the one on the bottom left is the ratio image of those 2. And as you can see, we're getting this fruit appearing nice and bright against the leaves. The leaves have almost disappeared from that image. So we can translate this into the orchard. This is an orchard shot. Filter 1 on the left, filter 2 in the middle, and the ratio image on the right, and you can just about start to see the fruit appearing. Nicely contrasted. The light wasn't particularly good on this day, I have to say. It just finished raining, and those little white dots are in fact raindrops. So if we want an automated system for harvest estimation, how can we move forward with this? So we can definitely use the spectral techniques to enhance the visibility and the contrast of the fruit against the leaf, particularly when it's immature fruit. But if we add 3D data, depth information, from either stereo cameras or LiDAR, and those are quite common pieces of equipment these days, we can build a 3D map of where that fruit is. And that's what's shown in that figure there. That's real data, by the way. Then we can count the fruit. Problem with manually counting fruit is that people make mistakes, there's double counting, and it's very slow and laborious. If we have the 3D location of the fruit, we can prevent that double counting and any accidental counting of fruit that we're imaging in other rows. So that initial orchard experiment, the best result we achieved was within 2.5% of the manual count over about 500 samples of fruit. This is very much work in progress, and there remain issues with the lighting and obscuration, but we believe the approach is very well suited to future automation, and it does work with any fruit. So that's the state of play with the harvest estimation. I'd now like to move on to the next project, which is about leaf roll disease detection in grapevines. This is a collaborative project between Callaghan Innovation and Plant and Food. And the aim of this project was to investigate whether we could use hyperspectral data to actually detect the presence of the leaf roll disease in the grapevines. A particular interest is white varieties like Sauvignon Blanc. The red varieties are usually amenable to conventional colour photography. And I'd certainly like to acknowledge my collaborators, Dr. Carmen Chui, Dr. Gareth Hill, Plant and Food at Mount Albert in Auckland. And I should point out that this project was funded by the Strategic Science Investment Fund from Plant and Food. So the methodology for leaf roll disease, this is a conventional colour image, but it's gleaned from the hyperspectral camera. And what we can do is we can pick a region of interest, each leaf, a small little rectangular region using the software, and we can interrogate that spectrally. Remember that each pixel in this image has its own spectrum, so there's a lot of information in each pixel, several hundred wavelengths. Now, if we pick a region of interest, we can get thousands of pixels, thousands of spectra. And then we can use the spectral analysis average over 10, 20, 30 leaves, and we typically use that sort of number for a particular state of vine. So we did some experiments with diseased and healthy vines. And then we look for correlations between the disease state and the spectrum. So this is these two graphs here, just to give you an indication of some of the issues that are involved when you're using natural sunlight outdoors. The one on the left here, the graph on the left, is what the sunlight spectrum looks like with this camera. So you've got the camera response overlaying this, but you've also got the rather detailed information that's contained in the spectrum from the sun. And this has absorption features in it due to gases in the atmosphere, like oxygen, water vapor. And the sun's atmosphere itself also introduces these absorption lines, Fraunhofer lines. So it's quite complicated, and if you try to use that as a white reference, and you divide one by the other, you can get into all sorts of trouble. So we developed a novel normalization technique, which I can't talk to you about, actually. But the one on the right there is typical of the image from a grapevine leaf. It's got information in it, particularly around where chlorophyll absorbs and reflects nicely. So that's a typical spectrum from the leaf on the right. And we looked at two different varieties, Sauvignon Blanc and Merlot. We had something like 30,000 spectra per vine type, and we looked at 24 different vines. So we had quite a large data set, and from that we were able to establish that there's a bit of a pattern here, an indication. I can't tell you exactly what the spectral features are, but the analysis that we did showed that there is definitely a difference between the diseased and healthy states, particularly for the Sauvignon Blanc, which is really an important find. For the Merlot, there is still a difference there, not quite so pronounced, and as you'll see if you go and visit Plant and Food's stand here, they're about to launch a conventional color camera technique for actually the red varieties, which has been very successful. So, but the white variety, that's still open to a lot of research, and this is part of that. So just to summarize the conclusions about the leaf roll disease detection, as I've said, the Sauvignon Blanc, it looks like we can detect the presence of disease with spectral techniques. Red varieties, yes, there's a difference there, although that's pretty much covered by conventional color camera technology. These data sets are very large, and they're full of information. I've only scratched the surface with the analysis I've done here, so we could really do with a much more in-depth, detailed analysis to pull out other features, perhaps. The data sets can get, say, quite large, between 3 and 4 gigabytes per image, so it's a big data problem. So we plan to do more measurements next year, just to build up our database. Ultimately, we'd like to develop more convenient systems to take into the vineyard. Typically handheld devices, but my preference is to actually put a camera system onto an automated platform like a robot, which moves up and down the vineyard and gathers an awful lot of data very quickly. And we also hope to be able to apply this to other diseases and perhaps even other horticultural species. So that's the leaf roll disease part. Here's another collaborative project which is about weed detection and discrimination. This is a collaborative project between Callaghan Innovation and Unitech, and the aim of this project was to see whether the hyperspectral technique could be used not only to detect weeds, but also discriminate different types of weeds in pasture. Now, this may not sound particularly relevant to horticulture because it was primarily aimed at preventing livestock from eating toxic weeds like ragwort, but it could be applied to any weed type. So that's why I've included it here. Ultimately, we want an automated platform to be developed which incorporates these results. So I'd certainly like to acknowledge my collaborators from Unitech. That's Wayne Holmes and Dr. Melanie Uy. Melanie's actually recently joined the University of Waikato. So the hyperspectral image acquisition for the weeds. This was done over a period of a year, quarterly intervals, 3 different soil types, 3 different types of weed. This is typically what we did, have a square meter quadrat, which we put in the field. That's a ragwort in the middle there. The top image is a conventional color image, and the one down below is a false color hyperspectral. 3 different soil types, as I've said. We use both cameras, so we cover both frequency bands, so we've got lots of data here. 3 types of weed, ragwort, gorse, and blackberry. I've given you the Latin names there, just in case you want those. Then natural daylight was used, so again, there are issues with using natural daylight. It does vary quite a bit as clouds come over and so on, but we were actually able to use that white reference data in this instance. That's what that white object is in the middle there. So the analysis, what this is a classification technique. So it's a very in-depth classification algorithm that's been developed. We looked at 2 different things. Very simple one-way ANOVA analysis, that's analysis of variance, and this thing called a boosted linear discriminant analysis, and that produced excellent results. I'm not going to go into the gory details of all that. If you want to read up on that, it was published recently in a paper at the I2MTC conference here in Auckland in May. I've given you the reference there if you want to follow that up. Here's a quick summary of the results. So what we're trying to do here is come up with algorithms which classify the 3 different weed types and separate them. You have a different algorithm for each weed, and this graph sort of just shows you how we separate those weeds from each other. Okay, so just summing up and looking ahead, hyperspectral imaging continues to be an active area of R&D in this country. Numerous applications for horticulture, and I've just sort of scratched the surface really, and based on my own experience with projects. I'm certainly happy to help those who are interested in exploring those possibilities. The way forward really, I think, is integration with automated robotic platforms, particularly for orchard work and in vineyards where there's a lot of ground to cover and a lot of data to acquire quickly. I think that's most likely route to market. I should also mention that the hemp and medicinal cannabis sector is fast emerging, as probably some of you are quite aware. Just wanted to draw your attention to Callaghan Innovation establishing a hemp working group to assist horticulturalists in this area. It consists of industry organisations, government agencies and research institutes. I've listed some of them there. I apologise if I've missed anyone out. If you want to find out more about that, just come and have a chat afterwards. And thank you for your attention.